Welcome! If you're hoping to learn about Kalman filters, you've come to the right place. In this lesson, you'll start off by learning about the background of the Kalman filter, what problem it solves, how it came about, and where you're likely to see it used. You will understand the challenges of localization and recognize the need for a filter. We'll then dive into how the Kalman filter algorithm works, first through a one-dimensional example and then a multi-dimensional example. You'll have the chance to implement both in C++. You will then learn a specific variation of the Kalman filter called the extended Kalman filter that extends its reach of applications even further. The Kalman filter is an estimation algorithm that is very prominent in controls. It's used to estimate the value of a variable in real time as the data is being collected. This variable can represent the position or velocity of a robot, or for example, the temperature of a process. The reason that the Kalman filter is so noteworthy is because it can take data with a lot of uncertainty or noise in the measurements and provide a very accurate estimate of the real value. And it can do so fast. Unlike other estimation algorithms, you don't need to wait for a lot of data to come in order to calculate an accurate estimate. Let's look at an example. Here, we're measuring the pressure that an underwater robot experiences as it swims through water. Recall that underwater, pressure increases linearly with depth. The pressure measurements are not perfectly accurate though. There may be fluctuations in the water causing fluctuations in pressure, as well as electrical noise from the sensor itself. As soon as the pressure sensors start collecting data, the Kalman filter begins to narrow in and estimate the actual pressure. In addition to the sensor readings, the Kalman filter also takes into account the uncertainty of the sensor readings, which is specific to the sensor being used and the environment that it is operating in. Now, you might be wondering, at a high level, what is happening every time a measurement is recorded? Well, that's a two-step process, and the Kalman filter is a continuous iteration of these two steps. The first step is a measurement update, which is exactly what it sounds like. We use the recorded measurement to update our state. The second step is a state prediction. We use the information that we have about the current state to predict what the future state will be. At the start, we use an initial guess. We continue to iterate through these two steps, and it doesn't take many iterations for our estimate to converge on the real value. In this lesson, we will dive into the implementation of each of these steps. By the end of the lesson, you will have an intuitive understanding of the Kalman filter algorithm, as well as be able to implement it in C++. The Kalman filter was invented by Rudolf Kalman at a very convenient time in American history. Soon after developing the algorithm, Kalman visited his acquaintance Stanley Schmidt at his workplace in NASA and introduced the algorithm to NASA staff. At the time, NASA was struggling to apply existing algorithms to the nonlinear problem of trajectory estimation for the Apollo program. The hope was to launch a spacecraft into a trajectory around the moon. The challenge lay in being able to create something accurate enough to guide the spacecraft through very narrow corridors of space, but also efficient enough to run on an onboard computer in the 1960s. At the time, computing power was very limited in both the onboard computer and the computer that was used for simulation and testing. Another challenge was that during the flight of the spacecraft, measurements would be coming in at irregular time intervals, something that the existing algorithms were unable to process. After a lot of work and even some tweaking of the algorithm, the Kalman filter provided the Apollo mission with the navigational accuracy to successfully enter orbit around the moon. Since its success with the Apollo program, the Kalman filter has become one of the most practical algorithms in the field of controls engineering. Today, the Kalman filter is applied in many different disciplines. Within engineering, the Kalman filter is often used to estimate the state of a system when the measurements are noisy. For example, the fluid level in a tank, or as you saw earlier, position tracking of a mobile robot. Outside of engineering, the Kalman filter is very popular in the field of economics. For instance, to estimate the exchange rate of a particular currency, or the global domestic product, a measure of a country's economic well-being. Computer vision is another big user of the Kalman filter for many different applications, including feature tracking. So far, I've been referring to the Kalman filter as one unique entity. However, there are actually three common types. There is the standard Kalman filter, and there are two variations to it, the extended Kalman filter and the unscented Kalman filter. The Kalman filter can be applied to linear systems, ones where the output is proportional to the input. The EKF can be applied to nonlinear systems, which is more applicable in robotics, as real-world systems are more often nonlinear than linear. The UKF is another type of nonlinear estimator, appropriate for highly nonlinear systems, where EKF may fail to converge. In this lesson, you'll be learning about the Kalman filter and the extended Kalman filter. If you wish to learn about the unscented Kalman filter, you will find some helpful resources provided. Feel free to keep these for future reference. Before we dive into the details of the Kalman filter, it's important to understand a few intricacies of robot operation that will give context to why a Kalman filter works the way it does. Let's explore two different robot worlds, the ideal world and the real world. In both worlds, the robots know their starting positions. In the ideal world, the robot is instructed to move 10 meters forward. The robot proceeds to do so and stops precisely 10 meters from its starting position. The movement was error-free. The robot in the real world is also asked to move forward 10 meters. In the real world, however, there are a few complexities that result in the robot's movement being imprecise. The robot may encounter imperfections in the terrain, experience wheel slip, or be adversely affected by other factors in its environment. Upon completion of its movement, the robot may not be at the 10-meter mark precisely, but some distance ahead of or behind of its desired goal. This error will be different with every movement performed due to the randomness encountered in the environment. Let's look at this movement on a graph. If we were to record the real-world robot moving 10 meters forward a total of 100 times, the results would look like this data here. The roboticist with a keen eye may notice that this data resembles a bell curve, also known as a Gaussian. This graph displays a probability distribution of the robot's final position after multiple iterations of the movement. The x-axis represents the distance traveled by the robot, and the y-axis represents how often the robot stopped at that distance. This curve shows that if we were to ask our robot to move, it is most likely to stop at the 10-meter mark, but at times can find itself as far off as the 12-meter mark. The shape of the Gaussian is specific to the robot and the environment that it is operating in. If the robot was driving around a factory floor, there would be fewer environmental factors to affect it, so its movement would be more precise and its distribution more narrow. On the other hand, if the robot is performing rescue missions, it may have any number of environmental factors affected, such as adverse weather or unexpected movements due to unstable terrain. The result is a much wider Gaussian distribution. But the distribution of the uncertainty is not the only problem here. If a robot were to continue to take blind movements, one after the other, then its location would become less and less certain with every movement. You can see this displayed on the graph. Every movement is uncertain, and these uncertainties stack up over time. With all of these uncertainties in motion, a robot needs a way to sense its own action. But unfortunately, sensory data is often uncertain too. Let's go back to our two robot worlds to explore this. Let's say that we are interested in knowing the speed of a robot, and that we have sensors on board the robot to measure this. In the ideal world, the sensor will measure the speed of the robot accurately, and respond to changes in the speed instantaneously. However, in the real world, sensor measurements will contain some amount of noise. An expensive encoder may come close to what you would expect in an ideal world, but if you're using hobbyist-grade robotic sensors, they will exhibit imperfect measurements. So now that we know that both movements and sensory measurements are uncertain, how can the Kalman filter help us make better sense of our robot's current state? The Kalman filter can very quickly develop a surprisingly accurate estimate of the true value of the variable being measured. For example, your robot's location in our one-dimensional real world. Unlike other algorithms that require a lot of data to make an estimate, the Kalman filter is able to do so after just a few sensor measurements. It does so by using an initial guess and by taking into account the expected uncertainty of a sensor or movement. There is another advantageous application of the Kalman filter. Let's say that your robot is using GPS data to identify its location. Today's GPS measurements are only accurate to a few meters. It is possible that by using the GPS alone, you cannot obtain an accurate enough estimate of your robot's location. However, if you use additional sensors on board the robot, you may be able to combine measurements from all of them to obtain a more accurate estimate. This is called sensor fusion. Sensor fusion uses the Kalman filter to calculate a more accurate estimate using data from multiple sensors. Once again, the Kalman filter takes into account the uncertainty of each sensor's measurements. So whether it's making sense of noisy data from one sensor or from multiple, the Kalman filter is a very useful algorithm to learn. Before we dive into designing a Kalman filter, let's make sure that we're on the same page when it comes to naming conventions. Since a robot is unable to sense the world around it with complete certainty, it holds an internal belief, which is its best guess at the state of the environment, including itself. As you may recall, a robot constraint to a plane can be described with 3 state variables: 2 coordinates, x and y, to identify its position, and 1 angle, yaw, to identify its orientation. These are its state variables, and we will denote a state with the bold letter x. States may change over time, so sometimes we will use a subscript to represent state x at time t. If you recall the 2 steps involved in the Kalman filter algorithm, they are a measurement update and a state prediction. Let's look at the first one. You know that a robot can perceive its environment using sensors, which produces a measurement. This is denoted with the letter z, and z of t represents the measurement obtained at time t. Next are control actions, such as movement, can change the state of our environment. Control actions are denoted by u, and u of t represents the change of state that occurred between time t minus 1 and t. Perfect. Now that we've agreed on the naming conventions, let's go back to the Kalman filter cycle. We need to start the cycle somewhere, and this is usually with an initial estimate of the state. As you will soon see, the estimate does not have to be accurate. It can be an awful guess, and the Kalman filter will still manage to give us good results very quickly. Then, we iterate between the measurement update, where we gain knowledge about our environment, and the state prediction, which causes us to lose knowledge due to the uncertainty of robot motion. You will first learn to implement the measurement update, and following that, the state prediction. Throughout this time, you'll be working with a one-dimensional Kalman filter. However, after gaining a better understanding of how Kalman filters operate, you will extend your knowledge to a multi-dimensional Kalman filter and even code one in C++. Once you're a Kalman filtering expert, we will look at how the extended Kalman filter allows us to solve a wider range of problems and help us with real-world robot localization. The new belief would have a mean somewhere in between the 2 Gaussians, since it is combining information from both of them. But where? What do you think? Would it lie precisely in the middle, or would it lie closer to one of the curves? Well, since the measurement update is more certain, the new mean will lie closer to the measurement update. Let's begin our Kalman filter implementation with the measurement update. Let's take a look at an example back in our one-dimensional robot world. It seems that a robot's been roaming around while we've been away learning. However, I have an inkling that the robot's current position is near the 20-meter mark. But I'm not incredibly certain, so the prior belief Gaussian has a rather wide probability distribution. Next, our robot takes its first sensory measurement, providing us with data to work with. The measurement data, z, is more certain, so it appears as a narrower Gaussian, with a mean of 30. Hey, our intuition was close. Given our prior belief about the robot's state and the measurement that it collected, where do you think the robot's new belief will be? By implementing the measurement update, you've now completed half of the Kalman filter's iterative cycle. Let's move on to state prediction next. Recall that state prediction is the estimation that takes place after an inevitably uncertain motion. Since the measurement update and state prediction are an iterative cycle, it makes sense for us to continue where we left off. After taking into account the measurement, the posterior distribution was a Gaussian with a mean of 27.5 and a variance of 2.25. However, since we've moved on to the state prediction step in the Kalman filter cycle, this Gaussian is now referred to as the prior belief. This is the robot's best estimate of its current location. Next, the robot executes a command: move forward 7.5 meters. The result of this motion is a Gaussian distribution centered around 7.5 meters with a variance of 5 meters. Calculating the new estimate is as easy as adding the mean of the motion to the mean of the prior. And similarly, adding the two variances together to produce the posterior Gaussian. Now, it's time for you to implement this in C++. Please add your code to the state prediction function. And when you're done, run the code on an example prior with a mean of 10 and a variance of 4, and a motion with a mean of 12 and a variance of 4. Alright, so we've learned a few things. The measurement update is a weighted sum of the prior belief and the measurement, and the state prediction is the addition of the prior belief's mean and variance to the motion's mean and variance. You've coded both of these steps, and now it's time to add some support code that will call them one after the other, as long as measurement data is available and the robot has motions to implement. For the purpose of this example, we will use two arrays to hold the measurement values and motions. The index of every value in each list represents its timestamp. The first value in the measurement array is the measurement at time equals 0. The second at time equals 1, and so forth. Here we have 5 values for each, so we will be able to go through 5 iterations of the Kalman filter cycle. At each iteration, the Kalman filter will try to estimate the state of the system. After 5 iterations, we will see if the Kalman filter converges on the robot's true value. We will also use two variables to represent the variance of the measurements and the variance of the motions. If you remember, we also require an initial estimate of the robot's position. In our motion example, the robot left off at the 35-meter mark, so let's use that as our initial estimate. We must also enter the uncertainty associated with this estimate. I've been keeping a close eye on our robot, and I can assure you that it hasn't gone anywhere. We can use a fairly certain value of 4, but as you'll soon see, this value isn't quite as critical to a successful outcome as you may initially think. Your task is to write the code that will iteratively go through the available measurements and motions and apply a measurement update or a state prediction to each one of them. That's your last step to implementing a one-dimensional Kalman filter. You've done a great job thus far, implementing the Kalman filter in one dimension. Now it's time to consider systems with higher dimensions. After all, most of the real-life processes that we'd like to model are multidimensional. For instance, the XY location of a robot. Let's step through what a multidimensional, otherwise known as a multivariate, Gaussian looks like, and then move on to code a 2D Kalman filter in C++. A 2D Gaussian can also be represented as so, where the contour lines show variations in height. We will be using two-dimensional Gaussians as examples, but the same concepts and processes that you learn here can be applied to higher dimensional Gaussians as well. For a one-dimensional Gaussian, the mean was represented by a single value, mu. For a two-dimensional Gaussian, the mean is a vector with two values, one for each of the two dimensions. An n-dimensional Gaussian would have a mean vector that is size n by 1. Similarly, while a one-dimensional Gaussian has a single value for the variance, a two-dimensional Gaussian has a covariance matrix, represented by an uppercase sigma. The covariance matrix represents the spread of the Gaussian in 2 dimensions. An n-dimensional Gaussian would have a covariance matrix that is of size n by n. The diagonal values of the matrix represent the variance, while the off-diagonal elements represent the correlation terms. An important fact to note is that the covariance matrix is always symmetrical. In the case of the 2D Gaussian, the two off-diagonal elements are equivalent. To make better sense of what a covariance matrix represents, let's take a look at a few examples of two-dimensional Gaussians. Let's fix our mean to an arbitrary point and manipulate the values in the covariance matrix. If the x and y variances are both small and equal to one another, the 2D Gaussian representation will be circular. In such a case, you are equally certain about the location of an object in each dimension. However, it's possible that you are quite certain about the location of an object in the x-axis, but not so much in the y-axis. In such a case, the contour lines of the Gaussian will start to take on an oval shape. Notice that the correlation terms are 0. If the correlation terms are non-zero, the two axes are correlated, and you will have a skewed oval as you see here. Depending on whether the terms multiply out to a positive value or a negative value, your oval will skew to the right or left respectively. Then, once you gain information about one axis, it will reveal information about the other due to the correlation. A multivariate Gaussian can be modeled with the following equation. D represents the number of dimensions present, and you'll notice that if you plug in D equals 1 into the formula, it simplifies to the one-dimensional Gaussian formula that you were presented with earlier. In our one-dimensional examples, the system state was represented by one variable. In n-dimensional systems, the state is a vector with n state variables. If we were to explore a two-dimensional example, these two state variables could be the x and y position of a robot. Or, if we're looking for a more interesting example, it could be the position and velocity of a robot. This leads right into another important matter. When working in one dimension, your state had to be observable, meaning that it had to be something that can be measured directly. In multidimensional states, there may exist hidden state variables, ones that you cannot measure with the sensors available. However, you may be able to infer their value from other states and measurements. In this example, the location of the robot is observable, while its velocity is not, making it a hidden state variable. However, a robot's position and velocity over time are linked through a very simple formula. Let's look at this on a graph. If initially the position of the robot is known, but its velocity is not, the estimate of the robot's state would look like so. A Gaussian that is very narrow in the x dimension, representing confidence about the robot's location, and very wide in the x dot dimension, since the robot's velocity is completely unknown. Next, a state prediction can be calculated. This is where the Kalman filter starts to get exciting. Knowing the relationship between the hidden variable and observable variable is key. Let's assume that one iteration of the Kalman filter takes 1 second. Now, using the formula, we can calculate the posterior state for each possible velocity. For instance, if the velocity is 0, the posterior state would be identical to the prior, and if the velocity is 1, the posterior will be here, and so forth. From this, we can draw a posterior Gaussian that looks like so. This doesn't yet tell us anything about the velocity. It just graphs the correlation between the velocity and the location of the robot. However, what do we have next? A measurement update. Let's see if it will be able to provide us with sufficient information to identify the velocity of the robot. The initial belief was useful to calculate the state prediction, but has no additional value, and the result of the state prediction can be called the prior belief for our measurement update. Let's say that the new measurement suggests a location of x equals 50. Now, if we apply the measurement update to our prior, we will have a very small posterior, centered around x equals 50 and x dot equals 15. This may look like magic, but it's the exact same measurement update that you applied before, implemented in 2 dimensions. Take a look. This was the prior belief, and here is the measurement. The posterior belief is just a weighted sum of the two, and more confident than either the prior or the measurement. Then, the relationship between the 2 dimensions narrows down the posterior for the x dot axis. After all, if the robot moved from x equals 35 to x equals 50 in 1 second, the speed should be trivial to calculate. And so it seems that 2 iterations of the Kalman filter cycle were enough to infer the robot's velocity. Continuing iterating through the measurement update and state prediction steps will update the robot's internal state to keep it aligned with where it is in the real world. Now, let's look at the linear algebra equations that enable this and apply them in the Kalman filter. Here are the Kalman filter equations that you've seen thus far. We'll be using them to take a look at the 2 extreme cases for a Kalman filter. The case where the sensor's measurements are perfect, and the case where the sensor produces completely uncertain data. Let's start with a perfect sensor. If the sensor that you are measuring with is perfectly accurate, then the measurement noise R would be a matrix of zeros. I will represent it as so. In such a case, the equation for S would be simplified to the following. When you plug the equation for S into the formula for the Kalman gain, you have the following equation. We can rewrite this equation. There is a helpful matrix property that allows us to apply the inverse not to the product of the matrices, but to the individual matrices. However, in the process, the order of the matrices in the product reverses. The result is the following equation.
Then, we can use another handy matrix property to simplify even further. The H transpose and the inverse of the H transpose are simplified to be the identity function, as are P prime and the inverse of P prime. The result is that the common gain is equal to the inverse of the measurement function H. This is important, so let's keep this in mind as we continue. The next equation in the Kalman filter has us updating the mean using the common gain. We haven't yet calculated the measurement residual, y, so let's plug in the equation for it. Now, we can replace k with what we calculated it to be earlier. From here, it's as easy as multiplying out the inverse of h to every term inside of the brackets, and simplifying the result. Once again, we can substitute the inverse of h multiplied by h with the identity matrix. Then, you'll notice that we have x prime and negative x prime in the same equation. These sum to 0, and the entire equation simplifies to x is equal to the inverse of h multiplied by z. H is the function that maps from the state to the measurement, so its inverse would map from the measurement to the state. The new mean is entirely made up from the measurement. We've thrown out any information that the state prediction provided because it's not needed. The measurement is perfect. The same can be shown for an utterly imperfect measurement, one that you know you cannot rely on at all. In such a case, R would be a matrix of infinities. The uncertainty is as high as it can be. I'll represent it as so again. Now, the equation for S contains the product of some matrices plus infinity. In such a case, S would equal infinity. Once again, we move on to the Kalman gain equation. Here, we can substitute S for infinity. And now we have the product of some matrices, including one that is the inverse of infinity, as in infinity to the power of negative 1. Well, that's 0, and anything multiplied by 0 is 0 itself. With a negligible sensor, the Kalman gain is 0. The equation for the new mean would only have one term left, and so x is equal to x prime. In such a case, the new mean is equal to the state prediction, and the measurement update is not included at all as it is unreliable. As you saw here, the two extremes for the Kalman filter are a perfect sensor and a negligible sensor. In these two cases, the new state is either exclusively dependent on the measurement or exclusively reliant on the state prediction. In reality, you will more often find that the Kalman gain is somewhere between the two. It is an averaging factor, evaluating which of the measurement update or state prediction should be trusted more, based on the measurement noise and the process noise. I hope that working through these two examples has demystified the Kalman filter equations just a bit. Once again, you need not remember these equations. They can be referenced from the lesson or textbook as needed. Alright, you've written a program that can apply the Kalman filter to real-life localization problems. You're a champ. It takes skills and patience to get this far. However, we've got a little bit further to go. If you recall, the assumptions under which the Kalman filter operates are that the motion and measurement functions are linear, and that the state can be represented by a unimodal Gaussian distribution. Well, it turns out that these assumptions are very limiting, and would only suffice for very primitive robots. Most mobile robots will execute nonlinear motions, for example, moving in a circle or following a curve. So what can we do if our Kalman filter can't be applied to most robotics problems? Let's take a look at why we can't apply the Kalman filter in more detail, and maybe we'll find some answers there. Here is a prior distribution, a unimodal Gaussian distribution with a mean of mu and a variance of sigma squared. When this distribution undergoes a linear transformation, for instance the function y equals ax plus b, the resulting distribution looks like so. This posterior distribution is a Gaussian with a mean of a mu plus b and a variance of a squared sigma squared. This is precisely what can happen in a state prediction. The important thing to note is that a linear transformation that takes a Gaussian distribution as an input will always have a Gaussian distribution as an output. Now, what happens if the transformation is nonlinear? Let's look at another example. Once again, the prior distribution is a unimodal Gaussian distribution with a mean of mu and a variance of sigma squared. But now, the function f of x is clearly nonlinear. The resultant distribution is no longer a Gaussian, as can be identified from its shape. In fact, the distribution cannot be computed in closed form, meaning in a finite number of operations. Instead, to model this distribution, many thousands of samples must be collected, according to the prior distribution, and pass through the function f of x to create this posterior distribution. What used to be a simple algebra or matrix manipulation has become much more computationally intensive, which is not the responsiveness that the Kalman filter is known for. So what can we do? Well, if you look closely, and I mean really closely, let's zoom in, you may notice that for very short intervals, the function f of x may be approximated by a linear function. This will allow us to use the Kalman filter on this nonlinear problem. The linear estimate is only good for a small section of the function, but if it is centered on the best estimate, the mean, and updated with every step, it turns out that it can produce sufficiently accurate results. The mean can continue to be updated with the nonlinear function, but the covariance must be updated by a linearization of the function f of x. To calculate the local linear approximation, a Taylor series can be of help. If you're not familiar with the Taylor series Wikipedia page provides a great summary, along with some helpful visualizations. A function can be represented by the sum of an infinite number of terms, as represented by this formula. This is called the Taylor series. However, an infinite number of terms is not needed. An approximation can be obtained by using just a few of the terms. And a linear approximation can be obtained by using just the first two terms of a Taylor series. This linear approximation, centered around the mean, will be used to update the covariance matrix of the prior state Gaussian. Let's take a look back at our nonlinear example and apply the linearization. The Taylor series can be simplified to a linear equation, one of the form y equals ax plus b, and the transformation can be applied to the prior. The result is precisely what we wanted, a Gaussian. It will inevitably have an error. You can see that the posterior Gaussian distribution is quite different from the distribution that you saw before. However, the trade-off is in the simplicity and speed of the calculation. Let's recap what the differences are between EKF and KF. To begin with, either the state transformation function, measurement function, or both are nonlinear. These nonlinear functions can be used to update the mean, but not the variance, as this would result in a non-Gaussian distribution. For this reason, locally linear approximations are calculated and used to update the variance. Before you dive into the formulas for EKF, it's important to generalize the process for multidimensional state transition or measurement function.
I'm really proud that you've gotten this far, because this content is a challenge to learn. You've implemented two Kalman filters, one for a single dimension and one for a multidimensional problem. You then learned how to apply the extended Kalman filter to nonlinear problems and are now ready to tackle the challenge of implementing the extended Kalman filter in ROS. I hope that you're feeling more confident about your ability to apply the Kalman filter to robotics.